Hi everyone, today we'll take a look at inverse functions. So if you briefly remember the earlier videos, I had pointed out what inverse function is and how can we define them. So most important for the inverse function is that it must pass the vertical line test. The vertical line test. If you don't remember what the vertical line test is, you can Google it, or you can watch one of my earlier videos where I've explained both the vertical line test and the horizontal line test. All right. Now, the second important thing was basically inverse. For a function to be inverse, it needs to be either 1 to 1, 1 to 1, or it must be an onto function. It must be an onto function. An onto function is, let's say you have um, a codomain of set B, which is your codomain. Every single value must be arranged for a specific input. Okay, so here my codomain is x, y, z, and w. All right. Now, for this to be an onto function, every single input must correlate to every single element in the codomain. Let's say if let's say B went to Z instead of W, I would say that this is not an onto function. All right, I hope that clears it up. Now, second important thing is that let's say our g of x is equal to the inverse of f of x. This does not mean 1 over f of x. Just remember that this inverse is not an exponent, it's just a notation, right? So I know it's a very silly thing for me to say, but if you are revising this or if you are learning this for the first time, um, I won't be surprised and I won't blame you if you do, misinterpret this for 1 over f of x. It's not equal to 1 over f of x. All right, so these are just a few basic things. However, I'm sure that you already have learned inverse functions. So let's get started with a quick and easy example question. All right, so just before we get into the inverse in examples, I just want to look at the method, or I've just kind of briefed it up. Okay, so let's say we have a function y equal to f of x. We just swap x and y for each other. So wherever there is y, we put x, and wherever there is x, we put y, and we write g is equal to x is equal to g of y. Same thing, but just interchange it, right? That's what we have done, interchanged it. All right. Now, we just solve for x, or we solve for g of y, right? Solve for x, or solve for g of y. That's it. Nothing else changes, all right? Okay, so we have this question. F of x is equal to 2x plus 1, okay? That's our original function, okay? So how can we do this? So let's convert f of x to y, just for the sake of simplicity, okay? Therefore, we have y is equal to 2x plus 1, all right? Super simple, nothing too crazy, okay? Now, if we replace this, what do we get? We get x is equal to 2y plus 1. Now we solve for y, okay? So we'll have x minus 1 by 2 is equal to y, all right? We've exchanged it and we've solved for y, or you can say this is the original x, okay? If you want to call it, you can call it the original x. I won't blame you for it, okay? So therefore, our inverse is x minus 1 by 2, okay? X minus 1 by 2. That's about it. Okay, super simple, nothing too crazy. This is how it's going to be for every single function, provided it meets the two original constraints that I'd said. Either it's a one-to-one function or it's an onto function. All right. Simple way to check that if it passes the vertical line test. Right. That's the best way to do it. Okay. All right. One more important thing. I haven't covered any trigonometry in this functions chapter. However, you might be asked to find inverses of sine and cosine and tangent functions. So the only way to solve those questions is by knowing your trigonometry and knowing your identities that exist in that chapter itself. There's no workaround for that. So you must be aware of such identities and all the properties that do exist as well. Okay, super simple question, nothing too crazy. You can now put in these values as your input, and you will get these corresponding outputs as well, right? You can test them out yourself. And if a question does get a little bit more complicated, let's say you have radical functions or reciprocal functions, the same process follows, right? You will just undo everything one by one. Don't forget your rules for equations. Whatever you do to one side, you must do to another, and you just move forward like this. All right. Let's look at a few more examples. All right. So we have a question here. If our f of x is x plus 1 by x, and we're supposed to find the inverse, right? The domain is given by 1 to infinity, and its corresponding range is from 2 to infinity, inclusive of 2, okay? So let's start, okay? We have y is equal to, sorry, let me just redo that. Let me just write it as x plus 1 by x, all right? Now what do? We replace x and y for each other, okay? So we'll have x is equal to y plus 1 by y. Okay, now what do? We multiply by y on both sides. We'll get xy is equal to y squared plus 1. Again, super simple, nothing too crazy. Okay, I'll bring everything on the right hand side, so I'll have y squared minus xy plus 1 is equal to 0. Okay, now what do? Well, nothing. We just solve for we just solve for y using the quadratic equation. So what do we have? We have y is equal to, well, what is the quadratic equation? Negative b. So we have x plus or minus the square root, and we have minus x whole squared plus 4 times 1 and 1 again, right? That's about it. Pretty simple, nothing too crazy. So we have all divided by 2, okay? So we'll have b squared minus 4ac. My apologies. This should be a negative. So this will go out. And this should be a negative. So we'll have x plus or minus square root of x squared minus 4 all over 2a. Okay? So now we can break this up into two cases. Case number 1, we have y is equal to x plus square root of x squared minus 4 all over, oh, I'm so sorry, why did I write 2a? Just 2, okay? And here we'll have y is equal to x x minus, this will be a minus, square root of x squared minus 4 divided by 2, all right? Super simple, this is case 2. Now, how do we know which one to take? Well, we have the domain and range given to us, right? So now the domain of the inverse is the range of the original function. Remember, in the earlier videos, I had mentioned this really, really explicitly. Anyways, I'll just write it down here. Domain of f inverse x is range of f of x, right? So, what would be the domain of this function? What's limiting my function here? Well, it's the radical part, right? It's the square root that's limiting it. Okay, so very simple. What's the property of a radical function? Well, everything inside the square root must be greater than or equal to 0. Well, in this case, let's see if we have space. Okay, we have space here. Okay, so we have x squared minus 4 in the square root. Well, we know this must be greater than or equal to 0. So if we square both sides, what do we get? X squared minus 4 is greater than or equal to 0. X squared is greater than or equal to 4. And x must be greater than equal to 2, or x must be less than equal to minus 2, right? That's what we have. So now so this works out, right? Both cases work out properly, that's fine, right? So now the next thing is, essentially, I know that this must be 2 to infinity, so we can take this one right here, and we neglect this area. Well, that doesn't really matter at the end of the day, because it works out for in both cases, right? We can take any value greater than 2 or any value less than -2. However, the range, or you can see the range is the domain, right? This is the range. So if we take this function, right, and if we take, let's say, 10 minus some 10 or square root of 10 squared minus 4, we'll get maybe at eventually we might reach a point where we get negative values, right? So at one point y may be negative, right? It may be negative. And if you notice, the domain consists of only positive numbers, right? So with that logic, we can neglect this solution. And what are we left with? Only the first solution, which is, let me write it here again cleanly. Therefore, f inverse x is equal to x plus square root of x squared minus 4 all over 2. Yeah, that's about it. So this is our final inverse, which matches the restricted domain and range that we were given in the original f of x. All right, so we have another question. We're given their domain and range, 1 to infinity inclusive of 1, and the function is f of x is equal to 2 raised to the power x times x minus 1. Okay, so let's take green for this one, and let's see, how would we start? So we're given y is equal to 2 times x minus 1. Well, the most ideal way to solve this would be to take log on both sides. So let's take log. So before I take log, let me just swap the values as well. So I have x is equal to 2 times y minus 1. All right. Now I'll have log x is equal to, wait, let me just make this a log. Or wait a second, I'll just clean it up a little bit. Okay, so I'll have y times y minus 1 times log base 2. All right. I mean, you can take anything. I've taken log of log base 10 at the moment. I mean, if you want, you can take a log base 2. So if I take a log base 2 here, this is basically equal to 1, right? This is equal to 1. So if, with this case, I have this situation. Now, what do? I expand. So I'll have, let's say, log base 2 x is equal to y squared minus y, right? Super simple. Let's take it on the other side. So we'll have y squared minus y minus log base 2x. All right, what do? Same thing as we did before. We do the quadratic equation. So y is equal to negative b, which is plus 1, plus or minus square root of negative 1 squared, which is 1, and minus 4ac, which should be plus 4 log base 2x. Is it? Yeah, okay, perfect. Okay, and divided by 2a, which is just 2. And now that we have this, we can just check if the range, again, we'll have to see if it's plus or minus. So using the same logic before, if we take a minus sign, then eventually we might reach to a negative value, because if once a function inside, once the thing's inside the radical, let me use my pointer here. Once this area, okay, my bad. So once this area starts becoming more than 1, this entire function will become negative, and our domain is only positive, because remember, this is the range of the inverse, so which is the domain of the original function. Do not mix them up, okay? So this is the range, which is domain, and domain is from 1 to infinity, and the only way we can get something equal to 1 or greater than 1 is if we keep a positive sign, and we neglect the negative sign. So finally, our inverse will be 1 plus square root of 1 plus 4 log 2 base 2 x by 2. Okay, in this case, you could have taken log base 10, you could have taken the natural log, you could have taken anything you wanted. It really doesn't matter, but the only issue would have been that you would have been stuck with this extra coefficient here, which would have made this entire thing really messy. So just to keep it really simple, I've used log base 2. Um, Usually what the IB does is oftentimes it says show that this inverse is equal to some output, right? It already shows you, it already tells you what the final answer is so that everyone gets the same answer and it's easier for them to mark your answer. Right now, so I mean, for the sake of practice, even if you took a log base 10 or natural log, it won't be wrong. It cannot be considered incorrect. Okay. All right. So we have done a few questions now. Now let's look at a few properties. Okay. Let's look at a few properties now. All right. Let's look at the first property of inverse functions. So for a function to be invertible, it must be bijective. Bijective is just a complicated or a cool term for which what it means, it must be 1-to-1, like I mentioned before, and it must be onto, right? That's all that it means, nothing else. All right, so let's look at the second function. All right, so let's look at the second property. The graphs of f of x and f inverse x are the mirror images of each other in the line y equal to x. I think you must have learned this property before as well. Nevertheless, let me give you a very quick and easy example. Let's say you have f of x is equal to the natural log of x, which is nothing but log base e. Now the inverse will be e to the power x. Okay. Now if I were to draw this function, let me change my color to white, and if I make the axes here, okay, these are my axes. And let's make the functions in blue again. So let's say I have my e to the power x coming like this, where this is my 0, 1, and I'll have my log function coming from here, going like this, 1, 0. Okay. Now if I just like this, sorry, it's not exactly perfect, but you guys get the idea. And then let me just make a line y is equal to x. Y is equal to x would be like this, right? So you can see that they're mirror images of each other. Basically, the x and y coordinates always swap. So we have 0, 1. They just swap with each other, so we have 1, 0. And you can put in anything you want, really. I mean, you can put x is equal to e, so y will be 1. I'm sorry, if x is equal to e, ln would be, yeah. So here, if x is equal to 1, y would be e. Perfect, right? That's how it works. And e is roughly 2.71. Okay, next property. So normally the points of intersection of f and f inverse lie on the straight line y is equal to x. However, it must be noted that f of x and f inverse may intersect otherwise also. So let me give you a very simple example. Let's say we have f of x is equal to log half, that's the base, x. So our inverse will be 1/2 raised to the power x. Or you can say 2 raised to the power minus x. Okay? And if I were to draw these functions, they would look sort of like this. Let me take white again for the axes. So you would have something like this. I apologize for not drawing straight lines. However, okay, so we'll have something like this, as our inverse. Okay, let me just change the color. Let me put in, maybe I'll put red. Okay, so I'll put red. This is my inverse, which is 2 raised to the power minus x. And let me take green for log base half x. So I'll have something like this. Like this. Okay, something like that. And as you can see, they have an intersection point right here. Okay, you can verify this with other functions, and you guys can use Desmos maybe. So Desmos is a great tool that you can use to check it out as well. Okay, all right. So let me give you a very quick example as well right here. Let me see if I have space. Okay, I don't have space. I'll just kind of squeeze it in here as well. I'll just erase this, and I'll write it here as well. So let me change color. I'll do blue. Okay. So let's say you have f of or y is equal to 1 over x, right? Or let's say, let me call it f of x. So my inverse will also be 1 over x, or it will be, yes, it will be 1 over x again, right? So now you can see kind of, if I were to draw the function, they would look like this, and they would intersect like that. All right, fourth. So in general, f of g of x and g of f of x are not equal. But if they are equal, then in majority of cases, either f and g are inverse of each other, or at least one of f and g is an identity function. All right, let me explain this with the help of an example. Okay, I'll take purple. So let's say our f of x is equal to ln x, right? Natural log of x. And our g of x is equal to e raised to the power x. Okay, so if I'm going to do f of g of x, what we're going to have is ln of e raised to the power x, which is just x, right? If we have something like this, this goes out here, and we're just left with x because natural log of e is just 1, right? So if you want, I can just put x times 1. Similarly, if I put g of f of x, you can see that we'll have e raised to the power ln x, which is just x. Okay, so essentially what we just had is an identity function in both cases. If we have a composite functions where both f of x and g of x are inverse functions, right? They're inverse of each other. Okay. Um, okay, let me take one more example, which is f of x is equal to x itself. So f of x is equal to x, and g of x is equal to sine x. All right. So in this case, x is kind of like the identity function, okay? And g of x is some other legitimate function that we have. Again, I haven't gone over trigonometry, but I'm sure you've already learned the basic understanding of what a sine function is and how it operates. So very quickly, if I have f of g of x, it's basically sine x, and g of f of x is basically sine x. They're basically the same thing. Not basically, they are the same thing, right? It's quite obvious. Okay, now, fifth one. If f and g of x are inverse functions of each other, then f dash of g of x is equal to 1 upon g dash of x. So this apostrophe that is here is kind of like the first derivative, okay? First derivative. Again, I haven't, you know, revised or explained about derivatives and calculus. However, I would assume that you may have gone over it. If not, you can skip this and maybe come back to it later. Just write it down for the sake of writing it down right now, and then hopefully it'll make a lot more sense later on. Anyways, let me just quickly show how this works, not with an example, but a general explanation perhaps. Okay, so let's say we have f of g of x like this. And if f and g are inverse of each other, then the composite will be an identity function, which is x, right? We know that. Okay, so if I'm going to differentiate this, I'm going to use a chain rule. So I'm going to get f dash, or first derivative of f of x, and then we do the derivative of g of x, which is g dash of x. And then if we take the derivative of x, which is just 1. So here we have differentiated this composite function with respect to x. Okay. Now if we divide by g dash x on both sides, what are we left with? Well, we're left with g of x, f of g of x is equal to 1 upon g dash of x. Again, this is kind of an overreaching property. It may be handy. There's no guarantee. I can't promise it. However, it's a good property to keep in mind, considering we do have a lot of calculus in our portion. Okay, so with these 5 properties, let's look at one final example question. So we're given that f of x is equal to x plus 1 whole squared for x is greater than or equal to -1. So the domain is restricted, okay? Even though we don't need any restrictions for this domain, the question has restricted to this domain. That's always an important thing to think of, okay? Oftentimes, questions would restrict the domain because they want a specific inverse, okay? So make sure uh, you always look at the restrictions. Okay, now if g of x is the function whose graph is the reflection of f of x with respect to y is equal to x, then g of x is what? Well, in simple English, it's literally asking for the inverse of x, right? It's literally saying that g of x is the inverse of f of x. Okay, so let's get started really quickly. Okay, so we have y is equal to x plus 1 whole squared. So let's swap x and y. We're left with y plus 1 whole squared. Okay, then if we take the square root on both sides, we'll have plus minus square root of x. And this is y plus 1. Okay, so then we have, sorry, let me cross this off. Y is equal to plus or minus the square root of x minus 1. Kind of like this, or if I want, I could write it like this as well. Minus 1 plus or minus the square root of x. Now, this is my domain for the inverse. I can say this is my g of x is equal to minus 1 plus or minus square root of x. So this is my domain for my inverse, which is the range of my original function. And the range of my inverse is the domain, okay? So if I'm going to make sure that my domain is always going to be greater than or equal to -1, which is the range of this, my x or my square root of x should always be positive. I shouldn't be subtracting, okay? So I will only go with g of x is equal to -1 plus the square root of x. Right, this will be my final answer, and I will neglect g of x is equal to -1 minus the square root of x. Okay, so this is my final answer. Pretty simple, nothing too complicated. Whatever that you have to find the inverse of, there will always be some pattern and there will always be some restriction. So always look out for those, okay? The simplest way to approach this question is the easiest way, right? We won't, for example, we didn't expand here, right? We didn't expand, we didn't open the, we didn't use the FOIL method and expand it. We just took the square root and we try to keep it as condensed as possible, right? Avoid adding too many elements to your inverse, because the moment you do, things start getting really hairy, they get really confusing, and chances of making a mistake, especially during the exam when you're on a timer, is pretty high. So again, that's about it. Inverse is not a complicated concept. I'm sure you've been doing it for um, your IGCSE maybe exams if you have been taking them, or maybe your